Let's go ahead and apply the divergence test to both of these series. The divergence test is something that we should always be thinking about. Maybe we don't always write down the result of the divergence test, but we should at least be thinking about it. So remember that the divergence test either concludes divergence or it's inconclusive. And if the divergence test is inconclusive, then we apply a different test. So the divergence test is nothing more than taking the limit of a sub n. So let's take a look at this first one here. We're going to take the limit as n, well, in this case, k. So the limit as k goes to infinity of the summand of a sub k. Well, this limit is indeterminate. The numerator is going to infinity, and the denominator is going to infinity. So what we're going to do is apply L'Hopital's rule. So we will take the derivative of the numerator, so that will be 1/2 k to the minus 1/2. We will take the derivative of the denominator, 1 over 2k, times the derivative of the inside, which is 2. So we have a little bit of cancellation there. And let's simplify this expression. So we have limit of, let's see, that k in the denominator down here, we're going to have to flip that. So we're going to end up with k to the 1/2 divided by 2. This k and this k to the negative 1/2 will end up being a product of k to the negative half multiplied by k, which will be k to the positive 1/2. And this limit is infinity. And what we know is that if this limit is not 0, the series must diverge. The only way a series can converge is if this limit is a constant. It doesn't necessarily, if that limit is 0. If the limit is 0, the series might converge. If the series has a limit that is not 0, the series diverges. So in this case, this first case, we got a limit that was not 0, so the series diverges. Now let's check the second one. We're going to take the limit as k goes to infinity, square root of k divided by k cubed plus 1. Once again, we have this indeterminate form. We get infinity over infinity, so we apply L'Hopital's rule. We will take the derivative of the numerator, the derivative of the denominator. So the numerator's derivative is this, 1/2 k to the minus 1/2. The derivative in the denominator is 3k squared. Let's go ahead and just rewrite this a little bit, simplify it. So we will end up with 1 over 6k to the 5/2. The k to the 1/2, this negative 1/2 is going to go to the denominator. We'll have k to the 2 times k to the half, which is k to the 2 plus 1/2, which is k to the 5/2. And this 1/2, that's a 1/2, so the 2 is pushed into the denominator. Now, this limit is 0. And so what we decide here is that the test is inconclusive. So this means that the series might converge or it might diverge. And I did not spell inconclusive very well. So let's try that again. Inconclusive. So again, if the divergence test is inconclusive, we need to apply another test. It means that the series might converge, but it also might diverge. So in summary, the divergence test either can conclude divergence if the limit is not 0. Otherwise, if the limit is 0, the test is inconclusive and further analysis is necessary.